As a simple first example of finding an instantaneous rate of change of something that has nothing to do with position or time, I want to think about a circle. So, do you remember what the equation is for the area of a circle? A equals pi r squared. Do you know why that's true? Or could you prove that it's true? Do you have an intuitive understanding of why that's true? We're not going to talk about that right now, but it's a good question to ask. What I'm interested in, though, is if you think of that area as a function of the radius, so as you change the radius, the area obviously changes. That makes the area a function of radius. If you think of it that way, then you can think of how fast is the area changing as you let that radius change. So if you let the radius start to steadily get bigger and bigger, how fast is the area of the circle changing? So what's the instantaneous rate of change of area with respect to radius? We're going to use the method of increments to do this. So we're going to let h, instead of being the increment of time, h will be an increment of radius. So we'll start out with a radius r, a circle with radius r, and then we'll let that radius go out just a little bit by a distance of h. So our increment of radius is h. Then to find the instantaneous rate of change of area with respect to radius, we find the area, basically the second area. So if we're letting the radius get bigger, then the bigger area minus the smaller area. So that's the change in the area divided by the change in the radius. So a of r plus h minus a of r divided by h. H is the change in the radius. That gives us an average rate of change of the area as we let the radius change from r to r plus h. And we'll calculate that out. But what we're going to do with it after we calculate it out is we're going to let that increment, the radius increment, shrink down to 0. So let h shrink down to 0. That will tell us exactly how fast the area is changing for any given radius r. And it comes out to 2 pi r. And interestingly, that's also, you'll probably remember, the equation for the circumference of a circle. You could ask why. Why does that happen? But we're not going to try to answer that right now. Why did you do that? That was a very specific example, the area of a circle. We could generalize that a little bit. That was a quadratic equation, a equals pi r squared, because the variable r was squared. So what if we did, instead of a equals pi r squared, y equals some constant times x squared? And we'll let the constant be any constant. I'll just call it a, little a. So y equals a times x squared. Let's find the instantaneous rate of change of that with respect to x. We do the same thing that we did with the area. We'll use y instead of a. So we'll use the value of y at x plus h minus the value of y at x divided by h. So now h is not an increment of time, it's not an increment of radius, it's an increment of x value, whatever x represents. Maybe you want to think of this as a parabola geometrically, that's fine. Or it could represent anything else that's quadratic, that just has a quadratic term. That's the power and the beauty of this in some sense. So we'll plug in x plus h for the x to get the second y value. And then we'll subtract off the first y value, which was just ax squared. We'll simplify all of that in the numerator. Then we'll divide by the increment of x. And that increment was h again. And when you do that, just like before, there's an h that factors out on the top, cancels out with the h on the bottom, and then you can let that increment shrink down to 0. And when you do, you get a nice simple equation. You get the rate of change of that parabola, that y equals ax squared. The rate of change of that with respect to x is just 2 times a times x. So from now on, if you just have a quadratic term and you want to find the instantaneous rate of change of that thing, you already know the formula. Just multiply 2 times whatever that constant is times x.